Hello everyone and welcome to our presentation. Today we are going to be talking about a topic that powers our entire world, energy distribution. Specifically, we'll be exploring how we can make it smarter and more efficient using a concept from discrete mathematics called weighted graphs. So, what is energy distribution? It is the entire complex process of getting electrical power from the generating stations through a web of substations, transformers, and transmission lines, all the way to you, the consumer. But this system isn't perfect. A significant challenge is power loss, energy that's essentially wasted as heat in the transmission lines. This is where optimization comes in. Our goal is to use this system in the most efficient way possible to ensure minimum loss, maximum efficiency, and reliable delivery. And the tool that helps us to do this is graph theory. To start us off, we have Karthik, who is going to explain how we can take a massive real world power grid and turn it into a simple, powerful mathematical model.
Thanks, Ashad. So, how do we model a complex power grid? We use what's called a weighted graph. It is a surprisingly simple but powerful idea. Here, first we represent every key location, like a power station, a major substation, or a city as a node, which is just a dot on the graph. Second, the transmission lines that connect these locations are represented by edges. And the third is the most important part in our presentation, that is weights. Each edge is given a weight. This weight is a number that can represent anything we want to measure, like the cost of sending power, or the actual distance between the nodes, the resistance in the line, or as we are focusing on today, the amount of power lost during transmission. Let's look at the simple example. Here we have four stations A, B, C and D. All are connected together. You can see the weights on each line. The line from station A to station B has a power loss of 5 kilowatt, but the line from A to D is more efficient with only 3 kilowatt of loss. So this simple model gives us all the data we need to start making smart decisions. So why do we go to all this trouble? Why is optimization so essential? Well, first, as we just discussed, it's to reduce transmission loss. As we already seen in the previous slide that 5 kilowatt loss is waste of energy and money. So we want to find the paths that minimizes that. Second point, it helps us maintain stable voltage levels because an unbalanced grid can cause blackouts. And the third point, it minimizes the cost of power delivery. Less waste means lower cost for everyone. And the fourth point, it prevents overload on any single line, stopping catastrophic failures before they happen. And finally, it allows us to build reliable and fault-tolerant networks. That is, if one line goes down, the model can help us instantly find the next best route. So we know why we need to optimize, right? Okay, next Divi is going to walk us through the technical process of how this optimization actually works.
Okay, thank you, Karthi. Let's see detail about the technical overview of optimization operation. The optimization operation contains 4 steps. How can we determine the best course of action? It contains 4 steps. We first model the grid as a weighted graph, as Karthik described. To represent the cost or power loss, we identify our nodes and edges and give them particular weights. Here, for our graph, the nodes are substations and consumers, edges are transmission lines, and the weight of the graph is cost or loss. The second step is we use robust graph algorithms on this model. Some of them may be familiar to us. We use the 𝗡cie algorithm to find the lowest path of the graph from one point to another. We use Kruskal's or Prim's algorithm to design the entire network from scratch, which is called finding a minimum spanning tree. Prim's algorithm is efficient incremental tree building. The third step is the edge relaxation. Edge relaxation is crucial for how these algorithms learn. Here, the algorithm is constantly explores and finds new routes while updating the best known path. It regularly asks, is this new path better than the one already I have? If it is, it replaces. Yeah, it replaces. It replaces it with the efficient route. Finally, the last is under the foremost step is we reach the output. After running the algorithm, it provides an optimized layout of power. It gives us the answer, the most efficient way to route power with the least possible loss. This may sound a bit abstract. Let's see an example which may seen by another person.
Thank you, Divya Prakash. Let's imagine a source station A needs to send 10 megawatts of power to a station C. Looking at our graph, we can send a couple of possible paths. First, the most direct look path from A to B and then from a B to C. If we add those losses, that 5 kilowatts on the first line and 2 kilowatts on the second line, the total loss for path is 7 kilowatts. But what about the another path? We could go from A to D, then D to B, then B to C. If we add up those losses, we have 3 plus 4 plus 2 for a total of 9. By comparing these two, it's obvious that path A to B and B to C is the optimal one. It has the lowest loss. This is a very simple example of a kind of a decision these algorithms makes millions of times a day. Now let us quickly look at how an algorithm like a digicross, which Divi mentioned, find this automatically. The goal of a digicross is to find the minimal loss of path from our station point station A to every other stations. It starts A with a loss 0 and look at this its neighbors. Seeing it can get to a B with a loss of 5 and D with a loss of 3. Now here is that edges relaxation we talked about. The algorithm essentially asks itself, can I find a better path to a B by going through a D? Well, the path D is 3 and the path to B is 4. That's the total loss of 7. Is 7 going through D better than 5 going directly? No. So it keeps that the original more efficient path. It's continuous this process until it has explored the whole graph. It finds the path to C by going through a B 5 plus 2 for a total loss of 7. The algorithm runs through all the combinations of confirm that the best path to a C has the loss of 7. Digicross is perfect for finding the best path from one point to another, but what if you are planning the entire network? For that, we use a different concept and Karunakaran is going to explain that.
Thanks, Dhanush. Exactly. Decentra's algorithm is for a single path, but the minimum spanning tree or MST is for building the most efficient network that connects all the nodes. The goal here is different. We want to find a set of edges that connects every single station but does so with the lowest possible total loss. This is incredibly useful when you are planning a new network layout from scratch. An algorithm like 𝗪𝗿𝗏 or Prim's would look at our graph and select the most efficient edges one by one without forming a cycle. So in our slide, we have edges A to D which has a loss of 3 kilowatts, D to C which has a loss of 2 kilowatts, and A to B which has a loss of 5 kilowatts. Now all the 4 stations are connected and the total loss of our entire network is just 10 kilowatts, the minimum possible. So this is just about the theory. This kind of optimization is also used in real world right now. In many critical applications like in smart grid management, it's used to automatically route power based on real-time demand. For renewable energy, it's essential for figuring out the most efficient way to get the power from a distant wind farm or solar plant to a city, and also it is used for fault detection. If a power line is damaged, the graph is instantly recalculated to find the next best route. As we just saw, it's used for transmission line planning and it is also used for load balancing to make sure no single line gets overloaded and fails. So as you can see, this is very powerful and practical application of discrete mathematics. I'll pass it back to Harshit to wrap things up for us. So thank you.
Thank you, Karunakaran. So, to summarize everything we have covered today, first, we have shown how complex energy networks can be effectively modeled as weighted graphs where nodes are stations and edges represent transmission lines with specific costs or losses. Second, the goal of this is optimization to reduce power loss, minimize cost, and increase the efficiency and reliability of the grid.